I have two lab questions before we get started.
All right, good evening, everybody. Hope everybody's doing well. What I put for the today and tomorrow for these two food sessions, instead of going, into sort of specifics, what I thought was just do some problem solving from the back of each of the chapters. I thought that might be the best way to go over the concepts and such like that. So that's what essentially we'll do. We'll do some problem solving from the back of the chapters, and that'll give us some time to talk about some of the different topics that can be found in chapters 13, 15, and then in proteins and enzymes in chapter 16. So we'll start with chapter 13 first, dealing with carbohydrates. And we'll take a look at this point of some parts of 13.61. And 13.61 talks about finding chirocarbons. So remember, chirocarbons are carbon atoms that have four different atoms or groups of atoms attached to them. And I'm cutting out, okay? Let's see.
I don't know if you can hear us, but you're kind of cutting out.
Everybody, there's still audio issues. Can you hear me?
Kinda. It's like the same as before, but we can still kind of hear you.
Assuming everything is okay.
Yeah.
Everybody else having any audio issues?
It's just like muffly a little bit, but we could hear you.
A little bit of a slow start. All right, let's try it. All right, so question 13.61 deals with trying to find chirocarbons in a compound. Chirocarbons are carbon atoms that have four different atoms or groups of atoms attached to them. And sort of the main idea coming out of this, and we'll take a look at this in terms of monosaccharides themselves in a few minutes, is that when you find that a carbon is chiral, for our purposes and for this course, what that means is that the organic compound is chiral. And what that also means, in addition to that, is that once we determine an organic compound to be chiral, that means for that compound, there is also a non-superimposable mirror image that exists as well. And the relationship between those two compounds is that they are a type of isomer. They are a type of optical isomer, what are known as enantiomers. Remember, enantiomers are two non-superimposable mirror images of each other. And as I said, we'll get into that in terms of monosaccharides specifically in a few minutes. So again, going back to question 13.61, it involves taking a look at just some general structures and finding chirocarbons. So let's take a look at a couple of examples. Here's the first. OH. to a CH, which has OH going up. Then it has a CH2 to the right. Then an OH connected to that carbon. All right. So here's our first example. Now, based on the idea that in order to have a chiral carbon, you have to have 4 different atoms or groups of atoms attached to that carbon. There are a couple of shortcuts that you can hopefully remember that will essentially allow you to eliminate some carbons very, very quickly. For example, CH3 carbons and CH2 carbons are never chiral. Now, why is that the case? The reason that's the case is because if you are a CH3 or if you're a CH2, can you or do you have 4 different atoms or groups of atoms attached to you? And the answer is no. If you're a CH3, 3 of the things attached to you are hydrogens. If you're a CH2, 2 of the things attached to you are hydrogens. So you can't have 4 different atoms or groups of atoms attached to you if you're a CH3 or you are a CH2. So if we take a look at the example here, the CH2 carbon to the left and the CH2 carbon to the right, we could eliminate very, very quickly because those 2 carbons cannot be chiral. The other shortcut to remember is that carbons in a double or triple bond are not chiral. Why are carbon atoms in a double or triple bond not chiral? Because if you're in a double bond, you think about it. If you're a carbon in a double bond, what's the maximum number of different things you can have attached to you? It's not 4. It's only 3. And if you're a carbon in a triple bond, what's the maximum number of different things that you can have attached to you? It's not 4, it's not 3, it's only 2. So with the idea of a chiral carbon being a carbon atom that has 4 different atoms or groups of atoms attached to it, carbons in a double or triple bond cannot be chiral. So that's the other shortcut to sort of remember as well. Now, for this example here, we've eliminated the 2 CH2 carbons here and here. So really what it comes down to is this carbon in the middle. Is it chiral or not? Here's how I would go about doing it. What are the 4 things attached to this carbon? You have hydrogen, you have OH, you have the left portion, which is CH2 connected to OH, and you have the right portion, which is also CH2 connected to OH. Are those 4 different atoms or groups of atoms? And the answer turns out to be no. This structure has no chiral carbons. What's the issue here? CH2OH to the left and CH2OH to the right are exactly the same. Those 2 groups to the left or to the right of the central carbon are exactly the same. And therefore, that middle carbon is not chiral. So this particular example here has no chiral carbons associated with it. But again, if you have questions, feel free to jump in. Just jump in with your audio or use the chat feature. Either way. Let's do one more example. Let's do this one here. Let's consider this structure here. And again, very simply, what we're trying to do here is we're trying to find if any of these three carbons that are present are chiral carbons. So let's start with the CH3. We know that the CH3 carbon cannot be chiral. Why? Because three of the things attached to it are all hydrogens. CH3 carbons can never be chiral. If I go to the C double bond O carbon on the right, the C double bond O carbon cannot be chiral. Why? Because it's involved in a double bond. And if you look at the structure here, what's the number of different things that are attached to it? It's not 4, it's only 3. But therefore, again, carbons in a double or triple bond cannot be chiral. So what does it come down to for this example? It comes down to looking at the middle carbon. So again, let's see how we would identify the 4 things properly, how we would properly identify the 4 things attached to this middle carbon. So we have H, we have NH2, we have CH3, and then we have C double bond O with the H. Are those 4 different atoms or groups of atoms? And the answer is yes. Those are 4 different atoms or groups of atoms. So this carbon in the middle is chiral. So this particular structure has 1 chiral carbon associated with it. Let's just do one more. I just want to illustrate something. Now, even though it looks like a pretty long structure, this is actually a pretty quick example. Because if you understand sort of the shortcuts that we talked about a few moments ago, we can eliminate a bunch of carbons very, very, very quickly. We can eliminate CH3s, those 2 carbons. And we can also eliminate all of the CH2 carbons. So what it really comes down to, again, for this structure is just this sort of carbon right here, CH1. The biggest mistake that students make in this particular case and with chiral carbons in general is that they would say very quickly that this carbon is not chiral because it's attached to 2 carbons. Carbon to the left, carbon to the right. But you have to sort of think of the idea that it's 4 different atoms or groups of atoms. So when you have something attached to a carbon, when you look at it to see whether it's chiral or not, and you have something attached to it that has something else attached to that, you have to consider that entire portion, just like we did in the first example. So if I'm looking at this correctly, and I'm doing the 4 things attached to this carbon correctly, the way that I look at it is H, Br, the entire left portion, and then the entire right portion. If I think about it that way, do you have 4 different atoms or groups of atoms attached to that carbon? And the answer is yes. Because to the left, you have CH2, CH3. To the right, you have CH2, CH2, CH3. Those are 4 different atoms or groups of atoms. And therefore, this carbon here is chiral. So I like this example just to show, because again, a mistake that students make a lot of times is they say, well, this carbon is not chiral because it's attached to carbon and carbon. You have to understand the right technique and identify the 4 atoms or groups of atoms. To the left or to the right, you have to consider those as groups. So this carbon over here is a chiral carbon. So one of the things you have to be able to do going forward is you have to be able to look at structures and to be able to identify chiral.
So that's important. Okay. Your default microphone is.
You actually sound better that way.
Okay. Yeah, I thought I had it right, but I guess it fixed it on its own. So great. All right. Any questions about the chirocarbon idea? Okay. All right. So let's go to example 13.64. Now we get this to right grade. All right. So what they want us to do here is they want us to look at two Fisher projections. For a compound and tell if they are identical or enantiomers. Okay. Now, when we talk about Fisher projections are used essentially to draw compounds that have one or more chiral carbons, where in a Fisher projection, the carbon chain is written vertically with the most highly oxidized group towards the top. What's the most highly oxidized group? It's the group that has the most carbon to oxygen bonds associated with it. And then essentially you find the chiral carbons where you have the vertical carbon chain and then you have horizontal lines that intersect with the vertical carbon chain. At those points of intersection, you generally have your chiral carbons. Now, in these types of questions, when they're asking you to identify whether they're identical or they're enantiomers, the trick is that the chiral carbon or the carbon that they're showing you in the middle may or may not be chiral. If that central carbon, because in these, if you're following along with the textbook, and as you'll see in a moment, essentially in these particular types of questions, you're looking at sort of one potential chiral carbon. If that carbon is chiral, then the other structure has to be an enantiomer as long as they're not drawn exactly the same. Now remember, there's two types of mirrors when drawing enantiomers. There's the vertical mirror. And remember, this is the mirror that's most often used because here the horizontal groups switch and the carbon chain remains in place. So the most highly oxidized group stays at the top, which is really by sort of connotation what a Fisher projection should do. Or you could potentially use a horizontal mirror where the vertical groups would switch. And it's possible to draw an enantiomer for a Fisher projection using a horizontal mirror. The vertical groups would switch. So the carbon chain, essentially, instead of having the most highly oxidized group towards the top, the most highly oxidized group would then end up on the bottom. Because whatever in that vertical sort of chain was that whatever's at the top would end up at the bottom, and whatever's at the bottom would end up at the top. As you saw in the notes, and as you'll see in a few minutes, when we look at monosaccharides, essentially, we always use the vertical mirror. But again, in the world of drawing enantiomers, you could use a horizontal mirror. All right. So let's take a look at a couple of examples. All right. Here's the first example. So here's one Fisher projection. This should be CH2OH, CH2, CH3. Sorry about that. I don't want to put it around. There's that. Let's get the pen back. Let's just bring that line up a little bit. All right. So here are two Fisher projections of the same compound. And again, in reality, it's got to sort of be the same. When I mean same compound, you know, in the idea of isomers, same chemical formula, okay? In this case, they're going to have the same connectivity, but are they identical or are they non-superimposable mirror images of each other? How would we figure that out? You can pick either structure to figure that out. Let me pick the structure on the left, all right? The only carbon that has the possibility of being chiral is the one where the two lines intersect. The CH2 carbon at the top cannot be chiral. It has two hydrogens attached. The CH2 carbon on the bottom cannot be chiral. It's got two hydrogens attached. The CH3 carbon connected to the CH2 cannot be chiral. It's got three hydrogens attached to it. So the only carbon that has the possibility of being chiral is the one in the middle. Is it chiral? Does it have four different atoms or groups of atoms attached to it? Well, what's attached to it? You have H, you have Cl, you have CH2OH, and you have CH2CH3. So is that four different atoms or groups of atoms? And the answer is yes. So that carbon in the middle there is absolutely chiral. So what that means is the only way this structure here could be identical, the only way the structure on the right could be identical to the structure on the left is if they are drawn exactly the same way. Because other than that, to come up with something that it looks different, you either have to use a vertical mirror or a horizontal mirror. Now, in this case, what mirror did they use? They used a vertical mirror. Because look what happened. Everything vertical stayed where it was. The Cl, which was on the right of the chiral carbon, ended up on the left. The hydrogen, which was on the left of the chiral carbon, ended up on the right. See how the horizontal group switched? So what's the relationship between these two structures? These two structures would be enantiomers of each other. These are non-superimposable mirror images. Let me go on and explain just a little bit further. Let's redraw the left structure again. But let's, for argument's sake, say that the right structure look like this. And the question was the same. Let's say the question was, what's the relationship between these two structures? Are they enantiomers or are they identical? Again, this carbon in the middle in the left structure is still chiral. So the only way the right structure could be identical to the left structure would be if they were drawn exactly the same. They're not drawn exactly the same.
Can you show an example with the line angle formula when you get a chance?
In terms of,
Like,
go ahead.
there was an example in the textbook on it. On page 442. Examples 11 and 12 both have line angle formulas.
Indicate each of the. Okay, yeah, I'll do one of those. Sure.
Okay, thank you.
No so again, just going back to this one. So unless they're drawn exactly the same, these two can't be identical. Notice in this case, okay, the H and the Cl stayed where they were if you're comparing left and right, but the CH2OH, which was on the top, now ends up on the bottom, and the CH2CH3, which is on the bottom, now ends up on the top. What type of mirror did they use to come up with this other structure? They used the horizontal mirror. Because if I use the horizontal mirror, right below the CH2CH3, that's what the mirror image would look like. And that's the structure on the right. So the relationship between these two is that they would still be enantiomers of each other. Before I go back and answer, Megan, your question, let me just show you one other pair of structures. All right. Suppose you had this. So this would be a separate example. And it's the same question. Would these be identical or would these be enantiomers? So it's the same question. Would they be identical or would they be enantiomers? How would I do it? Same way as before. I would look at one of the structures. Again, I look at the left one. And I want to see if I truly have a chiral carbon. Because a lot of the students would look at this right away and say that these are enantiomers. Because what they would notice is that it looks like a vertical mirror was used because the horizontal groups switch sides. The CH2 on the top and the CH2 on the bottom can't be chiral. So it comes down again to this carbon in the middle. And if that carbon is chiral or not. And it turns out that in this case, the middle carbon is not chiral. Because the four things attached to it are H, OH, CH2OH, CH2OH. This group and this group are exactly the same. So, no matter what type of mirror they use, if they draw it identical, if they use the vertical mirror like they did here, or if they were to use sort of a horizontal mirror, and it would look like that nothing changed if you use the horizontal mirror here, these two structures have to be identical to each other because there's no chiral carbon in either one of them. So basically, if I were to make the mirror image of the structure in the left, in other words, if you were to hold the structure up on the left to a mirror to see the mirror image, if you were to take that mirror image out of the mirror, you could superimpose them. So they're not isomers, they're not enantiomers, they're identical to each other. So even though it looks like I used a vertical mirror here, and I did, to come up with the right structure, if I were to take the right structure out of the mirror, it would superimpose for the left structure. So they're identical to each other. All right. So let me go take a step back. And it's about finding chiral carbons. But now, just to tell you, if I ask you to find chiral carbons, most likely I'm not going to give you a line angle formula. But because the Fisher projections a lot of times sort of use skeletal or line angle, whatever they call them, it's a good idea to understand it. So let me just do an example to illustrate how I would solve it for you. So sorry, just trying to find the page again. All right. So the example they give, and this is from 1311. This is 1311B, is the following. Now, here's what I would do if I'm going to solve this problem. What I would do is I would take this skeletal or line angle structure and I would convert it to either expanded or condensed. Because for me, in terms of finding the chiral carbons, that's going to be a lot easier to do. So if I was going to convert this into a condensed structure, what would I have? Well, if I go from left to right, I would have a CH3, which is going to be connected to a CH, which has a BR going up. The CH is connected to CH2, and the CH2 is connected to CH3. CH3, CH with a BR going up, CH2, CH3. These two structures are exactly the same. It should be a lot easier now to find if there are any chiral carbons. Okay, based on the shortcuts, we can take out the CH3s and the CH2 right away. So what does it leave us with? It leaves us with this one carbon right here. Is that carbon chiral? So again, if we're doing this properly, what are the four things attached to this carbon? Hydrogen, bromine, the CH3 to the left, and the entire right portion, which is CH2CH3. Is that four different atoms or groups of atoms? And the answer is yes. So that carbon right there is chiral.
Thank you.
You're welcome. So that would be my suggestion. And I know for the homework, there was one like that as well. And with the homework one, the carbon that had the OH to the left, that carbon had two CH3s attached to it, which made that carbon not chiral. The other carbon to the right that had the OH, that was a chiral carbon. And again, I think the easiest way to solve that would be to take it and make it into a condensed or expanded structure. All right. All right. So for the next couple questions, we're going to take a look at the monosaccharide known as D-glucose. One thing to mention, and I'm sure I talked about it in the notes, you don't have to memorize the structures of the monosaccharides. In other words, I'm not going to say draw D-glucose or D-galactose or D-glucose or such like that. But as you'll see in the next couple of examples, what we're about to do with this structure is what I would expect you to be able to do. So D-glucose has the following Fisher projection associated with it.
Is this a question in the textbook, or did you just make it up?
It's sort of going to be a combination of questions. This is D-glucose is from 13.69. So what we're going to do with this is sort of a combination of 13.69 and then 13.70 from the textbook. because there's a bunch of different questions we could ask you. And it's actually, I'm going to ask you one or two other things about this as well, outside of 13.69 and 13.72.
You said you're not going to make us draw these structures?
No, so I'm not going to say draw the structure of D-glucose.
Okay.
So the table in the textbook where it gives you the different monosaccharides, you do not have to memorize that.
Okay.
All right. So one of the things you should be able to do, and we'll call this letter A, is you should be able to classify this monosaccharide. Now, what do I mean when I say classify this monosaccharide? Remember, monosaccharides are classified as either an aldose or a ketose, depending on the type of carbonyl group that you have present, whether you have an aldehyde or a ketone, and then also based on the length of carbon chain. 3 carbons, triose, 4 carbons, tetrose, 5 carbons, pentose, 6 carbons, hexose. And as you saw, you put those sort of two ideas together, aldo or keto, and then the length of the carbon chain. So if we ask you to classify this monosaccharide, how would you come up with it? Well, first off, what type of C double bond O group do we have here? Do we have an aldehyde or a ketone? And hopefully you recognize very quickly that the carbonyl group here is an aldehyde. If you look at the top, you have a C double bond O carbon with a hydrogen attached, the C double bond O group with a hydrogen attached to the C double bond O carbon. That's an aldehyde. And then what's the length of the carbon chain here? You have 1, 2, 3, 4, 5, 6. Remember, Fisher projection for a monosaccharide, the carbon chain is written vertically with the carbons where the lines intersect, the chiral carbons essentially, where the lines intersect. So you have a 6 carbon chain. So you have an aldehyde that has 6 carbons. How would you classify this monosaccharide? You would classify it as an aldo hexose. Okay. So that you should definitely be able to do. You should be able to look at this structure and be able to classify it as an aldo hexose. Okay. So let's redraw. All right, what do we want to do here? Well, what we want to do is we want to draw, and I guess we'll call this B, draw the enantiomer using the vertical mirror and classify each structure as D or L. Because remember, for monosaccharides and for basically all the monosaccharides except for, a keto triose, for all the other monosaccharides, they are going to exist as enantiomers. The way we distinguish between the two, what are known as enantiomeric forms, the other way of saying it is the way we distinguish between the two enantiomers is one is the D version of the compound, the other is the L version of the compound. Now, I sort of gave it away in the previous slide where I said this is D-glucose. But let's talk about exactly how you would know this is a D, this is the D version of glucose. So how do we classify a monosaccharide as a D or L version? Remember, we look at the chiral carbon furthest from the C double bond O group. So if we number from top to bottom, carbon number 6 is the carbon that is furthest from the C double bond O group. But the issue with using that carbon to determine whether this is a D or L version is that that carbon is not chiral. So we look at the carbon above it, 5. And in fact, carbon number 5, that is the chiral carbon furthest from the C double bond O group. Off of that carbon, what direction is the OH going? The OH is going to the right. And because the OH is going to the right, off of that chiral carbon, what version of glucose must this be? This must be the D version. So again, if I gave this to you, you wouldn't have to know that this is glucose, but for this version and the enantiomer that we're about to draw, you should be able to tell that this is the D version of this monosaccharide. And again, the way we do that is we look at the chiral carbon furthest from the C double bond O group. Now, how do we draw the enantiomer? Using the vertical mirror. So remember, Fisher projections using the vertical mirror, everything vertical stays the same. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Okay. But all the horizontal, everything that's horizontal, the horizontal groups switch. And the key, because I saw this mistake made on a few of the homeworks, is that it's not just the horizontal groups on the last chiral carbon, the one that determines D or L. It's not only that OH and H that switch sides, it's all the OHs and Hs that are on the chiral carbons. All the horizontal groups on the chiral carbons switch sides. So for carbons 2 and 3, we're going to put the OHs to the left. I usually write it as HO. If you write it as OH, it's perfectly fine. You know, I'll assume that you know that the bond is between the carbon and the oxygen. For carbon 4, the OH is going to end up on the right. And for carbon 5, the OH is going to end up on the left. How do we know that this is an L version? Again, I'm still going to look at the same carbon, the chiral carbon furthest from the C double bond O group, which is carbon 5. But now notice the OH group is going to the left. And therefore, what enantiomer of this monosaccharide do we have on the right? Is it the D version or the L version? This would be the L version for this particular monosaccharide. Okay, so that's you should also be able to do. If I give you a monosaccharide, draw the enantiomer using the vertical mirror and be able to tell which one of the two is the D version, be able to tell which one of the two is the L version. You should be able to do that as well. Okay. Next. So let's stick with D-glucose. All right. C. Draw the alpha and beta anomers for D-glucose. Okay. Because remember, most of the time carbohydrates in general, including monosaccharides, don't actually exist in these open chain Fischer projections. They actually exist in cyclic or ring structures. And the ring structures that carbohydrates exist in are what are known as Haworth structures. And for monosaccharides, when a monosaccharide takes a cyclic form, there are two possible versions that exist for that cyclic form. There's what is known as the alpha anomer, and there's what is known as the beta anomer. And the only difference between the two cyclic forms is the direction that the C double bond O oxygen ends up going when it becomes OH. If it ends up going down, that gives us the alpha version. If it ends up going up, that gives us the beta version.
Is this the Haworth structures?
Yes.
Okay.
Yeah, so what we're going to do here is we're going to show you how to take this Fischer projection, and we're going to go through the steps to show you how to come up with the alpha and beta anomers. The two
Are
Haworth
we
structures.
drawing those on the test?
Yes. Yes. So we're going to go through that now with you. All right. So first thing I would do is, again, I would number the carbons. So 1, 2, 3, 4, 5, and 6. So we discussed in the notes that what usually happens is that when you have a C double bond O and an OH in the same compound, they tend to react with each other. Specifically for hexoses, the OH that reacts with the C double bond O carbon almost in the majority of the instances, and for our course, essentially all the instances, it's the OH on the last chiral carbon. That's the one that's going to be used to react with the C double bond O carbon. So, what were the steps that we talked about? Step 1. What we want to do is we want to take the Fischer projection and turn it 90 degrees. And I know I'm going clockwise, but it looks all right. I won't use my hands. We want to take the Fischer projection and we want to turn it 90 degrees clockwise. Remember, what distinguishes one aldohexose from another, right? What distinguishes between glucose, galactose, gulose? What distinguishes between all these aldohexoses? What distinguishes between all these aldohexoses are the directions of the OH groups on the chiral carbons. There's a difference somewhere of the direction of the OH groups on the chiral carbons. When you go from a Fischer projection to a Haworth structure, instead of having left and right off of the chiral carbons, when these carbons become part of a ring, we have up and down coming off those carbons. And remember, there's a direct correlation between left and right and up and down. Essentially, in your Fischer projection, right, an OH going to the right in a Haworth structure corresponds to an OH going down. And in the Fischer projection of a monosaccharide, an OH going to the left corresponds to a Haworth structure, the OH on that carbon going up. This first step will help with that correlation.
Can you just repeat that again? Sorry.
Sure. So so you have your Fischer. So this speaks to the OH groups on the chiral carbons. So you have your Fischer projection. And then you have your Haworth structure. And the correlation are the following. If you're going to the right in the Fisher projection, in the Howard structure, that OH should end up going down. And if you're an OH going to the left in the Fisher projection, in the Howard structure, you should end up going up. And the reason why we need this exact, so the reason why we have to have a defined correlation is because we have to maintain the difference between the aldohexoses, right? The difference is the direction of the OH groups on the chiral carbons. So it can't be arbitrary, the conversion from left and right to up and down. It has to be defined. And this is how it's defined. OH groups on the chiral carbons going right should end up going down. OH groups on the left should end up going up. The first step that we're about to do is going to help us with this correlation. So what we want to do is we want to take the Fisher projection and we want to redraw it horizontally from right to left. With particular focus on what? With particular focus on the chiral carbons. I'm not really concerned about carbons 1 and 6 because they're not chiral. I'm really concerned in a sense about carbons 2, 3, 4, and 5 because they are chiral. So for carbons 2 and 3, the OHs are pointing to the right. Think about it. If you're pointing to, think about a clock, right? If you're pointing to the right 3 o'clock and I go 90 degrees clockwise, what time do you end up at? You end up at 6 o'clock going down. So for carbons 2 and 3, the OHs are going to end up going down. For carbon 4, the OH is going to the left. So again, thinking about the clock, that's 9 o'clock. If I turn it 90 degrees clockwise, where do I end up? I end up at 12 o'clock. So the OH is going to go up. And then for carbon 5, the OH is again to the right. So after I turn it, the OH is going to be going down. And then don't forget about the hydrogens as well on each of those carbons. So upon doing that, our first step would be complete. Okay. Next step. We want to figure out what size ring we're going to draw. Whether we're going to draw a 6-atom ring or whether we're going to draw a 5-atom ring. Whether we're going to draw a hexagon or whether we're going to draw a pentagon. Now, how do I figure that out? You start with the C double bond O carbon. You include all the chiral carbons after that. And I'm going to include the oxygen of the OH on the last chiral carbon. So you start with the C double bond O carbon. You use all the chiral carbons after that. And then you use the oxygen on the last chiral carbon. How many atoms is that total here? 1, 2, 3, 4, 5, 6. So what shape am I going to draw? I'm going to draw a hexagon. Now, how do I start to do that? I'm going to put carbon number 1 all the way to the right, and then I'm going to start to make my hexagon. So carbon 1, carbon 2, carbon 3, carbon 4, and then I'm going to stop at carbon 5. Now, for carbons 2, 3, and 4, because remember, they're going to have one bond up besides the ring bonds. They're going to have one bond up and one bond down. To fill the OHs and the H's in on carbons 2, 3, and 4, I'm just going to go back to the picture above. So for carbons 2 and 3, I'm going to put the OHs down and the H's up. And for carbon 4, I'm going to put the OH up and the H down. Now, what about carbon 5? if you remember back to the lecture notes, we talked about the fact that for carbon number 5, even though the correlation would tell us to put the OH going down, if that OH were truly going down, we would not have the correct geometry for a hexagon. And what happens is that rotation takes place on the last chiral carbon before the ring forms in order to get this oxygen right here in proper position for the ring to form. And we said that this rotation is consistent from example to example. And that's why for carbon 5, I didn't attach carbon 6 yet. Because now I'm going to fill in what's attached to carbon number 5 based on this idea. And what does that rotation end up giving us? Well, carbon number 6 always ends up going up off of carbon 5. The hydrogen on carbon 5 always ends up going down. And the OH on carbon 5 always ends up going to the right. But I'm anticipating my ring forming, and therefore I'm leaving off the hydrogen on that oxygen. Because now, in order for the ring to form, what has to come off of the oxygen on carbon 5? Hydrogen. It's got to come off. Where does that hydrogen end up? One way to think about it is that it's going to end up on the C double bond O oxygen. And that will give us the new OH group. So let's make the ring. We're going to bond the oxygen off carbon 5 to the C double bond O carbon, which is carbon number 1. Carbon number 1 is now part of a ring. So besides the ring bonds, it has one bond up and one bond down. What happens to the C double bond O oxygen? The double bond can no longer be there. Because if a double bond was still on carbon number 1, that carbon would have too many bonds. As we talked about in the notes, and we just mentioned a few seconds ago, what happens to the C double bond O oxygen? It becomes OH. One way to put that OH would be going down. What's the last thing attached to carbon number 1 that we still would have to fill in? Hydrogen. Now, what anomer have we made here? Because I've chosen to put the OH going down off of the former C double bond O carbon, which we know can also be referred to as the anomeric carbon when you have these Howard structures. Because the OH is going downwards off of the anomeric carbon, what atomer of glucose have I made here? This would be the alpha anomer. This would be the alpha anomer. Now, how would I come up with beta? Well, essentially, almost everything should be exactly the same. So if you go back, I'll just look back for a second, if you look at the alpha anomer, I just basically almost copied it. Exactly what we just did. Because the only difference now to draw the beta anomer is when I bond the oxygen on the last chiral carbon, carbon 5, to the former C double bond O carbon, which is still carbon number 1. The other possible direction, the OH, the C double bond O oxygen becomes OH. The other direction that OH group could be going is up. And the reason why you have these two structures is that just like you cannot rotate around the carbons in a double bond, you cannot rotate around the carbons in a ring. And now, because the OH is going upwards off of the former C double bond O carbon, because the OH is going upwards off of the anomeric carbon right here, what atomer have I made here? This would be the beta atom. This would be the beta atom. Okay? So one of the things that you should definitely practice, and you have the monosaccharides in the textbook, the aldohexoses, and even a ketohexose as well, is you should be able to take the Fisher projection and draw the alpha and beta atomers, just like we did here. That is an expectation that I do have of you, so you should be able to do that. All right. All right. What else can we do with D-glucose? Let's do two other things. Couple of reactions of monosaccharides. The first of which is oxidation. So we talked about the fact that for monosaccharide, and if we were to ask you this reaction specifically, it would be about drawing the product of monosaccharide oxidation. We'll get to the carbohydrate in general idea in a few minutes. When a monosaccharide essentially undergoes oxidation, even though it has aldehyde, essentially, and alcohol groups that can both undergo oxidation, what usually happens is that a selective oxidation occurs. Most of the reagents that are used for monosaccharide or carbohydrate oxidation in general will focus on the aldehyde portion of the structure. And as we know, what happens when an aldehyde undergoes oxidation? An aldehyde becomes what? An aldehyde becomes a carboxylic acid. So if I was to draw the structure of the product here, everything would stay the same. But now, instead of having the C double bond O carbon connected to just H, for the carboxylic acid, the C double bond O carbon is going to be connected to what? OH. And that would be the structure of the product here.
Just to make sure, back on the last slide, you're going to give us the Fisher projection, and then we have to make the
alpha, beta. Yeah, so basically, I'm going back to this slide here for a second. You'd have the monosaccharide, and the question would say, draw the alpha and beta atomers for this monosaccharide.
Okay, just making sure.
Yep, absolutely. Okay. So, carbohydrates in general, which undergo oxidation, in other words, they reduce the other substance. They are reacting with, are called reducing sugars. When a carbohydrate undergoes oxidation, the substance that it's reacting with, that's causing it to undergo oxidation, that the carbohydrate is classified as a reducing sugar. The trick is, in a sense, is that essentially, in order for the carbohydrate to undergo oxidation, it's got to have an aldehyde group. The only way you can tell whether a carbohydrate has an aldehyde group is by looking at a Fischer projection. Because remember, as you just saw with the Haworth structures, the C double bond O group is gone. But most of the time, carbohydrates exist as cyclic or Haworth structures. So as we talked about in the notes, and I want to discuss here, can you tell from a Haworth structure whether you have a reducing sugar? And the answer is yes. So how do we tell from a Haworth structure if you have a reducing sugar? You need a quote-unquote free OH group on an anomeric carbon. And this applies to monosaccharides, disaccharides, trisaccharides. It applies to all of them. You want to look at the Haworth structure. You want to find the anomeric carbons. Now, how do you find the anomeric carbons? The anomeric carbon, whether it's a 5-atom ring or a 6-atom ring, the anomeric carbon is always going to be to the right of the oxygen in the ring. That's always going to be where you're going to find the anomeric carbon. What does a free OH group look like? Well, very simply, it just looks like OH. As you hopefully understand, what makes it free is that it's not involved in a linkage to another monosaccharide. Because as you saw, and we'll discuss a little bit again in a few minutes, most of the linkages involve either the oxygen on one or both of the anomeric carbons that are present, because each monosaccharide, if you're looking at a disaccharide or even a polysaccharide, we're not going to really focus at all on polysaccharides. We didn't talk about them. But we're talking about disaccharides. Each monosaccharide has an anomeric carbon. Remember, even for fructose, when you look at the Haworth structure of fructose, even though fructose is a ketohexose, when you look at fructose and the Haworth structure, you notice that you have a free OH on the anomeric carbon. It reflects the fact that fructose is a reducing sugar. It does a structural rearrangement to convert the ketone into an aldehyde. You wouldn't be able to tell that from the Fischer projection. But based on this idea of finding a free OH on an anomeric carbon, you would be able to tell that fructose is a reducing sugar. So reality, you should be able to tell from a Haworth structure of a monosaccharide and even a disaccharide, we'll talk about that in a few minutes, whether you have a reducing sugar or not. All right. The last thing to do with glucose, deglucose, is the other reaction. And the other reaction for monosaccharides that we talked about is reduction. Yes, I know when we discussed aldehyde and ketone reduction back in chapter 12, I was opposed to using hydrogen and we use sodium borohydride, NaBH4. I guess in this case, I'm still somewhat opposed to it, but in this case, we'll just follow what the textbook does. So if you see a monosaccharide and you see H2, you're going to want to remember that we are talking about reduction. So what happens to the carbonyl group when it undergoes reduction? What happens to an aldehyde or ketone when it undergoes reduction? The double bond between the carbon and the oxygen becomes a single bond. And then I'm going to add two hydrogens, one to the oxygen, the other to the oxygen-bearing carbon. And then for the monosaccharide, everything else that's present would remain exactly the same. OH and H. Sorry, meant to make that OH and then OH, OH, H and OH. That's pretty tough to draw there. Sorry about that.
So can ketones not be oxidized or reduced?
Well, ketones can definitely be reduced. That's absolutely the case. Just give me 1 second, and then I will go back over that. So yeah, so this would be the problem. So if you had something like this, CH2OH, C double bond O, and let's see, had OH, OH, CH2OH, and then H and H, and then you had reduction H2. Remember when we talked about aldehydes and ketones and we talked about their reduction? Absolutely, ketones can undergo reduction. That's absolutely the case. So to draw the product, again, the double bond between the carbon and the oxygen would become a single bond, and then you would add two hydrogens, one to the oxygen, the other to the oxygen-bearing carbon. And therefore, for the rest of the monosaccharide, everything else would stay exactly the same. So that absolutely can happen. The trick with carbohydrates and oxidation is the fact that all monosaccharides are reducing sugars. And the reason for that is essentially that even if you have a ketone in the monosaccharide, it actually undergoes an unexpected structural rearrangement in the open chain form that converts the ketone into an aldehyde group, and then it undergoes oxidation. So that's what makes it a little bit tricky. That's why the idea of looking for the free OH on the anomeric carbon in the Howard structure is so useful, because there's no C double bond O group present. If you notice, for every monosaccharide, if you were to draw any monosaccharide, every single monosaccharide, whether it's an aldose or a ketose, essentially the ones where you have the Howard structures, they would have a free OH group on an anomeric carbon. So they would be able to undergo oxidation. In terms of ketoses, really fructose is the main one that's discussed. I don't really know if there's too many other ketoses that are essentially discussed. It's really all about the aldoses, but it does turn out that all monosaccharides, even the ones that are ketoses, are reducing sugars. Now, as we're about to discuss, not all carbohydrates are reducing sugars, because when you get into the disaccharides and polysaccharides, when you have a ketone group, then the structural rearrangements no longer tend to occur. And again, that's going to be reflected by not having a free OH on an anomeric carbon like you saw in sucrose. And we're about to talk about that, sort of finish up our discussions this evening in a few minutes. All right. Other questions? And I'm just trying to find the table that has the different monosaccharides. I just wanted to check out the list for a second to see if I thought they had given a table that had the different monosaccharides. Fisher projections. Yeah, I thought they had given a table of the different monosaccharides, but I don't know if they do anymore. But you don't have to memorize them, so not overly concerned. All right. All right, so last part of the chapter. All right, disaccharides. Disaccharides are formed when two monosaccharides are linked together. What type of functional group do you have? You get an ether. An ether links monosaccharides together. You get an ether group to link them together. Remember, for your ethers, COC. All right. So, again, I'm not going to ask you to memorize the structures of disaccharides. In fact, I'm not going to ask you to take two monosaccharides together. I'm not going to ask you to take two monosaccharides and even put them together. We did that in the notes because I think it's important to see that aspect, but we're not even going to really ask you to do that. What we're going to need you to be able to do is to look at a disaccharide structure and tell three things. First off, you got to be able to name the linkage. Now, how do we name the linkage? You give the carbon numbers involved and alpha and or beta if the linkage involves an anomeric carbon or anomeric carbons. Based on the notes, there are three linkages that I expect you to be able to recognize. There is the alpha 1,4 glycoside bond or glycoside linkage. There is the beta 1,4 glycoside bond. And there is the alpha beta 1,2 glycoside bond. Now, in reality, my hope is that you'd be able to take sort of this information and be able to sort of even do above and beyond these three. But in reality, these are the three that I would sort of ask you about on an exam. If I gave you the structure of a disaccharide, I would say, I wouldn't say I would give you the structure, and it would have one of these three linkages, and you'd have to be able to come up with which one of these three linkages it is. And we'll sort of do an example in a moment to try to illustrate this with you. So that's the first. Number two, is the disaccharide an alpha anomer, a beta anomer, or neither one? And then three, and in a moment I'll explain why I'm jumping right to three, is the disaccharide a reducing sugar? And the reason why I like to lump these two together is we answer both looking for a free OH on an anomeric carbon. We're going to be looking for the same thing to answer both questions. Because if we have a free OH on an anomeric carbon, if it's going up, we know we're looking at a beta anomer. If it's going down, we're looking at an alpha anomer. If I don't have a free OH on an anomeric carbon, then that disaccharide doesn't have alpha and beta anomers. It only has one version. And if there's no free OH on an anomeric carbon, then the disaccharide is not a reducing sugar. If it does have a free OH on an anomeric carbon, then the disaccharide is a reducing sugar. So we're going to be looking for the same type of thing. All right. Let me just see if I can. I was looking for a structure of a disaccharide. Let's see if we can get one here. That's something different than. Let's see. All right, so I got an example. All right, so let's take a look at 13.41. All right, and I'm going to look at, let's look at structure A. Structure A with one change. And I'll discuss why I'm making this change in a moment. So let me draw out the structure. Now, when I draw out the structures of the disaccharides, I like to draw out the carbons. You know, the textbook, of course, loves skeletal line angle, whatever they're called, because it's just so much quicker. I'm not a big fan. Sometimes skeletal is really good. Sometimes it's not so nice. So let's draw this out. I'll show you more how, if I were to give you this structure. And again, you wouldn't have to know how to come up with the structure, but if I gave you this structure, we're going to do those three things that we discussed with you. All right. So here's the disaccharide structure. All right. So first off, letter A, let's name the linkage. Now, one of the things that you sort of need to be able to do this is you want to be able to number the carbons in the ring. So for a 6, the way I remembered how to do this is as follows. For a 6-atom ring, the carbon to the right of the oxygen is always carbon number 1. So for the left ring, this carbon right here would be carbon number 1. For the right ring, this carbon right here would be carbon number 1. If you had a pentagon, a 5-atom ring, as you saw in the notes, the carbon to the right of the oxygen is not carbon number 1. Which carbon number is it? It's carbon number 2. And then you would go clockwise from there. So 6-atom ring, the carbon to the right of the oxygen is carbon number 1. 5-atom ring, the carbon to the right of the oxygen is carbon number 2. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. So, first off, what carbon numbers are involved in the linkage? Well, for the left monosaccharide, it's carbon number 1. For the right monosaccharide, it's carbon number 4. So this is sort of some sort of 1,4. Now, is either one of them an anomeric carbon? Because if it is, then we have to use alpha or beta to give the direction the linkage is going off of that carbon. Sorry about that. We have to give the direction.
I just have a quick question.
Yeah, go ahead.
You said 5 carbons, you mean in the ring, not including the one outside?
Correct. So in other words, if you had something, and I'll just jump ahead for a second. If you had something like this, whereas you have like a ketohexose, in this case, the carbon to the right of the oxygen would not be 1, it would be 2, because carbon 1 would be outside of the ring. So you'd have, this would be 2, and then you'd have 3, 4, 5, and then 6 would be this way as well. So to the right of the oxygen for the 5 atom ring, that would be carbon number 2. All right. So is either one of these carbons an anomeric carbon? And the answer is yes. Carbon number 1 is the anomeric carbon for the left ring structure. Carbon number 4 is not an anomeric carbon. So we don't have to give the direction the linkage is going off of that. We only have to worry about carbon number 1 in this case. What direction is the linkage going off of carbon number 1? It's going up. How do we refer to up? Do we use alpha or beta? We use beta. So this linkage would be a beta 1, 4 glycoside bond. All right, so that's letter A. Letter B. Is this disaccharide an alpha anomer, a beta anomer, or neither one? How do we answer that question? Do we have a free OH on an anomeric carbon? In this structure, there are 2 anomeric carbons. Here's the first. Here's the second. Does this anomeric carbon have a free OH? No. Why? Because the oxygen off of that carbon is involved in the linkage. Notice COC, ether. It's involved in the linkage. But does this anomeric carbon have a free OH? Yes. What direction is the OH going off of that carbon? Down. And therefore, what anomer of this disaccharide are we looking at? Are we looking at an alpha anomer or a beta anomer? Well, this disaccharide is an alpha anomer. So the reason why, and if you look at the example in the textbook, I changed the direction of the OH here, because one of the things I want to make sure everybody understands is that you could have an alpha anomer where the linkage is a beta linkage, because the way we came up with these, in a sense, is different. You know, the linkage is based on these 2 carbons. The disaccharide is based on this carbon and this carbon, but we didn't look at this carbon because it doesn't have a free OH. It's based on this carbon. So the linkage here is a beta 1,4, but this disaccharide is an alpha anomer.
Can you just explain again how you got the beta 1,4?
Sure. So you notice how the 2 carbons that are involved are 1 and 4? Mm-hmm. Carbon number 1 is the alpha anomer for the first monosaccharide. So if your linkage involves either 1 or 2 anomeric carbons, you have to use alpha and or beta to give the direction of the linkage off of that carbon. So 4 is not an anomeric carbon, so we don't have to specify up or down, alpha or beta. But carbon 1 is an anomeric carbon. So we have to specify off of this carbon, is the linkage going up or down? What direction is the linkage going here? It's going up. What do we call that? We call that beta.
So
that's
it's literally going up, not based on the OH.
no.
Okay.
No. In other words, the linkage is here, involves this carbon and this carbon. When we go to look for the free OH, yes, I did look at this carbon here, but it doesn't have a free OH. This one does. So this one here answers question B. If you go back and look at sucrose, in sucrose, the linkage involves both anomeric carbons. If you look at the structure of sucrose, there's no free OH on an anomeric carbon. So that's why you could tell that sucrose is not a reducing sugar. But this one is, because one of the anomeric carbons, not this one, but this one, has a free OH. And it also tells us it's an alpha anomer. So letter C would be, is this a reducing sugar? And the answer is yes. This disaccharide is a reducing sugar. And again, the answer comes based on the fact that you have a free OH group on an anomeric carbon. It tells us that this disaccharide is a reducing sugar. So again, for disaccharides, this really sort of is my expectation, that you're able to look at the structure of a disaccharide, be able to name the linkage, tell whether the disaccharide is an alpha anomer, a beta anomer, or neither one, and to tell whether the disaccharide is a reducing sugar or not.
So we're not going to have to actually create the linkage?
No, I won't ask you to do that. The reason why is that sometimes it's not so obvious of how the monosaccharides link together. So I know we did that in the notes because I think it's important to work through that at the beginning. But from my perspective, now it's about looking at the disaccharide itself and being able to tell these three things. So you won't have to put a disaccharide together from two monosaccharides. Or like I won't say, what monosaccharides are present here. I won't ask you that as well. All right. Any other questions about carbohydrates? Because I think we're actually... Go ahead.
A question about the two labs that
Yes.
I do tomorrow.
Sure.
In lab 8, they never gave the pH of the detergent.
Don't worry about it. You can leave it blank.
Okay. And then for lab 9...
Go ahead.
How would you know if the protein reached the isoelectric point?
Okay, so if you look at the lab itself, it talks about methyl red. Okay. When you add methyl red to something and it turns yellow, you have a pH of a certain value. When it turns red or pink, you have a different pH value. What you want to do is you also want to look at the lab, and they give you the isoelectric point of egg albumin, which corresponds to a pH. So in other words, when you add the methyl red to the egg, it's yellow. That means the pH is at a certain value. When you add the acetic acid to the egg with the methyl red, what you probably saw in the video, or should have saw in the video, is that the methyl red goes from yellow to pink. That corresponds to a different pH. The question is, does that pH that it now reached, is it where the isoelectric point, which also corresponds to a pH, is it where the isoelectric point of egg albumin is? So in other words, if methyl red is yellow at a pH of, let's say, 6, and it turns to red pink at a pH of 4.5, and let's, for argument's sake, the pH, the isoelectric point of egg albumin, which would be, let's say, a pH of about, let's say, 4.9. Based on this information, if you added acetic acid to the egg and the egg went from yellow to red/pink, would you have reached the isoelectric point based on the information on the slide? What do you think?
Yeah.
Correct. Because since it changed color from yellow to red or pink, it means that the egg went from a pH of around 6 down to a pH of about 4.5. If the isoelectric point is around 4.9, 4.5 is lower than 4.9, we had to reach the isoelectric point. So use the information in the lab where it talks about what pH methyl red is at yellow versus red pink. And it also gives you the isoelectric point of the egg to answer that question using the ideas that we just talked about here.
Okay, I must have missed it somewhere, and that's why I was confused.
That's okay. It's in the lab. It's in the procedure part of the lab. I think it's right in where, if you look at the procedure part, right for that part underneath it, there's 2 tables that give you all this information.
Okay.
If you still have
yeah.
can't find it, just let me know.
Found it. All right. Thank you so much.
Of course. Other questions? All right. So tomorrow, I'll be on at about 12:15. We'll do lipid questions, and then hopefully there'll be time. We'll do some amino acid and protein questions as well. I'm working on your chapter 15 homework. My plan is to have that back to you. It's due tonight, don't forget, but hopefully I'll have it back to you late Friday, early Saturday at the latest, all right? So have a good night. Hopefully you can join tomorrow. I'll post the video for tonight a little bit later on once it uploads, and hopefully we'll see everybody tomorrow.
Do you think the test is going to be more...
I think
based?
Say that again, I'm sorry?
Is the test going to be like heavy on one topic than the other, or is it kind of all combined?
No, it's going to be even spread out between the carbohydrates, lipids, and then amino acids and proteins.
Okay.
It'll be evenly spaced.
Okay. Thank you.
You're welcome. All right. Anything else? All right. Have a good night, everybody. Hopefully we'll see you tomorrow.